start the randomly here any moment.
You didn't realize why he is like always late.
Zone 4.
Because he's off campus.
He's too cool.
This is my first class.
Yeah, because
class gets here like 20 minutes before class starts.
So, I'm going to try to take a fairly quick pace.
Who's talking about you? How are you? You know what happened yesterday?
Oh my goodness.
It snowed.
Christian.
Landon, that is the correct answer.
Thank you.
It's so wrong.
So, proposition 7.2.1. Let L be a linear transformation from vector space V to vector space W. Then what? 1, L of 0 is equal to 0. 2, L of a linear combination is equal to the linear combination of the images. Okay, so linear transformations take 0 to 0, and linear transformations, in some sense, preserve linear combinations. Let's prove that. Yep.
Can you do another step and pull groups of I outside of the summation?
No.
Okay.
So here's one. L of 0 plus 0 is equal to what? It's equal to what? L of 0 plus L of 0 by additivity. But on the other hand, this is what? 0. That's just L of 0, right? So I have L of 0 is equal to L of 0 plus L of 0. So if you subtract L of 0 from both sides, we get that L of 0 is equal to 0. So there's proof 1. Proof 2. Let's see here. So first of all, n equals 1. We have L of C1 V1, and that's equal to C1 L of V1 by what? Homogeneity of L. I'm trying to prove something, for natural number n. I'm going to use induction here, okay? So let's suppose it's true for n. Now I need to consider the n plus 1 case, right? So okay, so by definition of finite sum, this is C what? Cn plus 1, Vn plus 1, plus the sum . So that's just the definition of the finite sum. Then I can use, what can I use to make my next step?
Additivity.
Additivity, right. So additivity gives me that this is L of Cn plus 1, Vn plus 1, plus L of the sum from 1 to n. Again, it's additivity of L, which is one of the things we're assuming. By definition, L is a linear transformation if it's additive and homogeneous. Now I use homogeneity again, and also the induction hypothesis, right? So induction, at homogeneity right here, pull that constant out. And then the induction hypothesis to bring the sum out here. And then what? What is this? Well, this is nothing more than the sum I equals 1 to n plus 1 of Ci L of Vi. Again, by definition of finite sum, which we made recursive at the start of this course. Okay, hence 2 follows by induction. There you go. There is a relatively careful proof that a linear transformation of a linear combination is the same, excuse me, a linear transformation, the image under a linear transformation of a linear combination is in fact the same linear combination of the images. So you see even the weights are the same, right? Like the weights of this linear combination are C1 through Cn. The weights of this linear combination, again, are C1 through Cn. Yeah. So L of Vi is the image of Vi under L. Okay, guys? Just a little bit of language. So this is the image of Vi under L. All right, so proposition 7.2.2. If S subset of V is linearly dependent, then L, and I'm getting tired of writing this, so let me say L is an element of LVW. That's my shorthand for just saying that L is a linear transformation from V to W, okay? As L of S, well, not as, maybe that word here would be gives. L of S, what's still the wrong word? If, then, grammar, fine.
Are you arguing with yourself?
Yes. Suppose L is a linear transformation from V to W. V and W will be vector spaces throughout this whole lecture, so let me stop saying that, or writing it at least, all right? So suppose L is a linear transformation from V to W, and S is a subset of V, is a linearly dependent set. Then L of S is a linearly dependent set. All right, so proof of this. So what does it mean for S to be a linearly dependent set? Basically, just
Based on the same vectors that are scalar to vectors that make up V.
it means that there exists a V in S such that V is equal to a sum I equals 1 to N Ci, let's say Si, for S1, Sn in S. In other words, there exists a linear dependence in S. There's at least one vector V, which you can write as a linear combination of other vectors in S, right? Yeah.
So would you maybe prove this by doing something like an SJ, showing that it can be written, cannot be written?
I'm proving it right now, so let's watch. So, thus, L of V is what?
the summation.
Right. But what did we just prove by proposition 7.2.1 part 2? We could pull the constants out, right? And then what do we have then? So what I've shown you right here, this equal to that, if you call it star. Star is a linear dependence in where?
All of this.
Yeah, in L of S, right. Thus what? Proposition follows. We've just shown that the image is a linearly dependent set. Which linear dependence is responsible for it? It's the same one that you started with. Yes, Christian? So Landon, was that what you were?
No, I'm wrong.
No, okay. That's okay. Theorem 7.2.3. States the following. Again, a linear transformation. This time from B to W. Okay, same old. L, an element of linear transformation from B to W. Then L is injective if and only if what? L of x is equal to 0 if only if x is equal to 0. Put some brackets around here to emphasize that's a single statement. In other words, the only thing that maps to 0 is 0 itself. So this is a biconditional claim, right? So we should try to prove both directions. If you search your heart, you'll realize we've proved this before. Where did we prove it?
Chapter 5?
Chapter 5, but what was the difference?
I don't know.
The difference was that V and W were just RM
column.
and, yeah, there's column vectors, right? But in fact, the same exact proof follows through here. Right? So I will do one of the directions this time, which way you want me to go, forward or backwards? Okay. Forward? Okay. So assume L is 1-to-1, which is another word for injective, right? And suppose L of x is equal to 0. But L of 0 is equal to 0. First thing we proved today, right? So we have L of 0 is equal to 0, but 0 is also equal to L of x, which implies that 0 is equal to x by injectivity of L. And that proves the forward direction of the plane. Thank you, Chris. You picked the easy way for me. But the reverse proof that we gave last time still works here. Okay. We have miles to go before we sleep, though. Let us go on. All right, so.
Why don't we go before we sleep?
Yes.
Doesn't that mean we're not sleeping for like 2 months?
I guess it depends how fast you walk.
These are miles, not miles.
Oh. I'm sorry.
Oh, I don't worry about finals in here. Like, I already passed the final in this course years ago.
Gee, thanks.
Do you grade yourself? Because I know you take the final with us. Do you grade yourself?
Are they taking on the final is the grade?
So
I
theorem
think that's the answer sheet.
7.2.4. Trying hard not to get fished in here. If L is a linear transformation from B to W yet again, right? Then two things. Number one, if V naught is a subspace of V, then L of V naught is a subspace of W. Two, if W naught is a subspace of W, then the inverse image of W naught is a subspace of V. Or in other words, linear transformations take subspaces to subspaces. And also the inverse image of a linear transformation takes a subspace to get, again, another subspace. I'll give you guys a second to catch up. I see many of you are still writing over there. Something about we're about to prove something about a subspace, right? We don't have any explicit formulas, so span and the null space trick, those seem like they're off the table, right? Pretty much the only tool we're going to work with here is going to be what? The subspace theorem. Yeah, subspace theorem. There you go. So, yeah.
So like, is it saying if this was in the context of matrices and you did a linear transformation on like a matrix, and so that would be a subspace of the whatever the W is, and then the inverse of that matrix also be a subspace. Is that kind of what it's saying?
Inverse image here is not like an inverse matrix. This is a set theoretic inverse. Like, it's possible that L is not injective, and yet we still define inverse image. It's a set theoretic inverse image. So it may be a little bit different than what you're thinking off the top of your head, but in any event, let's prove this. So, number one. So what do? Assume that V naught is a subspace of V, right? And then we want to show that the image of V naught is a subspace of W, right? So what we should do then is let, let's say, I don't know, pick some letters here, alpha and beta be elements of the image, right? And let C be a real number, all right? Okay. What does it mean for alpha and beta to be in the image of L of V naught? What does that mean?
They're mapped from a V naught value variable.
Right. Okay. So let's come up with a name for them. Hence, there exists, let's say, x and y. I guess maybe I could use A and B. That'd be pretty good notation. Let's say A and B in where?
In V.
In V naught. In V naught. Such that what? L of A is equal to alpha, and L of B is equal to beta. By definition of image of V naught, L of V naught, this is what that means. Right? L of V naught is the set of all possible outputs under L of inputs from V naught. Anything that's in L of V naught must come from something in V naught. So then what am I supposed to do? Consider, what am I supposed to consider? I'm supposed to consider, say, C times alpha plus beta. What would I like to show?
That's a single element in
Oh, it's an element of L of V naught.
You want to show us a subspace, right?
I started with this assumption, right? Back here. I think some of you said it. I'm just going to write it down here. This is what our goal is to what? C times alpha plus beta is an L of V naught, right? That's our goal at the moment. So I've messed up my typesetting. Consider C alpha plus beta. What's that equal to? C times L of A, right? Plus L of B. Now what do I do? Yeah.
Use linearity of linear transformations.
Right.
So that's L of CA plus B.
Right, so Daniel's proposing we use the homogeneity and the additivity together, right? Referred to as linearity. And then what can I observe then? That this is what? This is an element of what?
V naught.
Now how do you know that?
Because V naught is a subspace, and A and B are elements of V naught, and C is.
Right, precisely. Because A and B are taken from V naught, we know that a linear combination of them is again in V naught, because V naught's a subspace. But what's that show?
And that's an element of V naught.
Right. Now that is that is a dangerous word. So specifically, that is C alpha plus beta. C alpha plus beta is an element of V naught. As a general point of order, it's almost always bad to use pronouns in proofs. Which is the math. Is it that? A lot of times those are ambiguous.
Will we use it all the time? Wait, no. I should go back to yours.
Did I ever use this here? I mean, look at my proofs.
No, I said definitely. Doesn't matter.
I mean, we use them, but it's for conversational purposes more so than anything else.
So we said that CA plus B is an element of V naught. Why?
Say it again.
CA plus B is an element of V naught. Why?
Because A and B are in V naught. We assumed that V naught was a subspace of V. That means it's closed under addition and scalar multiplication, of which this is both. So, see, I just used that this, but it was not ambiguous because I was pointing.
So A and B is the preimage of alpha and beta?
A and B are the preimages of alpha and beta. Yes, true. Very good. Oh, and then hence by the subspace theorem, we've got it. L of B naught is less than or equal to less than or equal to let's see, subspace of W.
Wait, where was W other than that last one?
Well, I mean, L of V naught is by definition a subspace of the subset of W.
Well, I guess like when we prove it, we need to have that somewhere.
I mean, I've shown that this set of things, I mean, I guess I should, well, this is the thing I was telling you guys. I may, on occasion, forget to mention the very important precondition of the subspace theorem, which is that the subset is actually a subset, right? So it is, by the definition of image, codomain, all that, it's clear that this is a subset of W from the start, because I wrote up here that L is a function from B to W.
Thank you.
So, yeah.
I was so confused.
Don't be
Now
confused.
I
Do
Yes.
we need to show L V9 is non-empty?
Oh, good point.
That's not
You're right. I should take a point off this.
No, you take 2 points. I was want to help you make sure that you didn't get that 1 point off. Knowing that it was subject.
Notice L of 0 is equal to 0, and 0 is an element of V naught. Hence, 0 is an element of L of V naught, which is not equal to the empty set of things. So, yeah, the fact that 0 maps to 0 is kind of important to this. Yeah. So the next one here, let's assume, let's try to go the other way. W naught is a subspace of W. then let's see here. Let x and y be elements of L inverse of W naught, which is, by the way, a subset of V by definition. Probably would be wise for me to restate state the definition of the inverse image of L under W naught, since classically speaking, this is something you guys have trouble with. Let's see here, L inverse, and I speak of you guys in the stereotypical sense of all linear algebra classes everywhere. Okay, so what is this? This is, in particular, this is like x and v, such that what? Such that L of x is where? W naught. So that's the set of points in the domain whose images fall in W naught. That's the definition of inverse image. Okay, so we know what? We have L of x and L of y are elements of what?
W naught.
W naught, right? If my use of x here is confusing, put a bar on it. There you go. Because this x and y up here were specific ones. I really shouldn't use x again here in a generic sense, sorry. So if this is x and y, I picked 2 points. I'm trying to show that the linear combination of those is again in the inverse image, because then by the subspace theorem, that will show it's a subspace. So let's see here, what can we do now?
Could you do the same thing as the other one? Constant.
Well, yeah, I want to,
But you have to do it.
how about this? If we look at, consider, how about this? Notice that, what is it? It's your C times L of x, well, please stay down here. C times L of x plus L of y is an element of what?
W naught.
Now, how do you know that that's an element of W naught?
Because if two things are an element of their by additivity, they have to be in that
Right.
recipe.
Well, because W naught's a what? What did we assume?
It's a subspace.
A subspace, right. Since W naught's a subspace of W, that's why we know that that's again in W naught. So then what? C times L of x plus L of y is actually equal to what? L of cx plus y by linearity of L, right? Which means that's what? That's also an element of, I mean, they're equal. We just saw it was an element of W naught, right? So again, this is an element of W naught. What does that say about cx plus y?
Element of inverse image of W naught.
They are an element of V, it's true, but that's not specific enough.
Element of inverse image of W naught.
Yeah, they are in the inverse image of W naught because their image goes to W naught, right? So that means the Cx plus y is an L inverse of W naught. Ah, therefore, oh man,
You just showed it to me.
I gotta show it's not empty. You gotta stop me. But what? Again, L of 0 is equal to 0, and 0 is an element of what? W naught, right? So what's that show?
That is not
If L of 0 maps to W naught, why do I know 0 is in W naught? W naught is a what?
Subspace.
Subspace. Is 0 in subspace? Yes, it is. So that means that, I mean, you guys were like, what are you talking about? Okay, fine, so to make this a little bit more clear, this is 0 in V, right? This 0 over here is the 0 in W. We're not talking about the same 0 necessarily.
But the fact that the zeros are there because of the fact that they're subspaces.
Right, and the first thing we proved today. I mean, that's how I know that's true. So that shows that 0B is an element of the inverse image of W naught, which thus is non-empty, right? Hence by subspace theorem. L inverse of W naught is a subspace of V. These are pretty typical test questions.
Oh, boy.
I'm sorry, is it too soon?
No, it's just.
Yes, I agree. This is difficult when we first see it. What makes this difficult is it's like the backwards thinking in this one, right? This one I think is the friendlier test question. This one here, right? Because you can start where you start at the beginning. If you know your definitions, you just write down what you want to prove. You apply linearity. It falls out, right? Here you have to kind of be a little bit more cunning, right?
Or you guys just memorize all the proofs.
You could just memorize all the proofs, but that seems a lot harder to me. I don't know. If you know the definitions carefully, it's not that hard to prove this thing, really.
Thank you for informing us that they might be on a test.
I mean, I've done it before. So I'm telling you.
I mean, thank you.
I don't enjoy grading these when I put them there. I'll tell you that.
So why do you think you don't know what you're
Because this is linear algebra, and if I don't test linear algebra, it's hardly a linear algebra class. All right, let V and W be vector spaces. If T is a linear transformation from V to W, like so, number one, this is a definition, okay? So the kernel of T is equal to the inverse image of 0. 2, the range of T is the image of T. It's the image of the domain.
I hate the word kernel.
Why?
I don't know. It's painful.
I always think of the Monty Python sketch where the mafia goes to threaten the military about the tanks. Shame if anything happened to them. No one knows the sketch. Anyway, T, V and W, linear transformation, then range of T is a subspace of W, and the kernel of T is a subspace of V. This comes from just looking at the sort of the very silly subspace of 0. The inverse image of the 0 subspace is the kernel. And the image of the whole space, the whole domain, is the range. And these proofs hold in those cases just the same. Right? In fact, these proofs are easier. If you wanted just to prove the corollary rather than like for generic subspaces, the proof is actually easier. Sometimes I'm nice on the test, I might ask you to just prove those. It takes away some of the annoyances of these two proofs we just went through. Definition. The dimension of the kernel is equal to what's called the nullity of T. The dimension of the range is called the rank. Now, we've used those words before, haven't we? But when I use them Wednesday, I use them with respect to a specific matrix. Now I'm talking about them with respect to a linear transformation.
They work with linear transformation and it's not a matrix.
It remains to be seen why using the same words are reasonable.
So they're completely different.
At the moment, they're logically quite different, yeah.
Do they still equal the same amount of dimensions as the transformation?
Oh, it would be very bad form for me to use the same words and not have it be justified in the end, you know? So there will be a reason that they're in fact the same thing, but yeah.
But like, is there like some reason that matrices and linear transformations and all this are all like so closely related? Or
Yes, we're getting to that. So anyway, but that's there you go, definition of nullity and rank for a linear transformation. I see I have spent too long for the proof today. Don't worry, that's Monday.
I mean, I love reviews.
That's a review from the future. All right, here's where we are.
Oh, I thought you meant longer. You're still on here.
So the next theorem that I would prove for you if I had infinite amount of time to prove theorems in class is this one. If you have a linear transformation, the following two conditions are equivalent. Following two. Oh man. Oh.
I'll take a point out of that.
Oh no. I think there are three here. So, injectivity of a linear transformation. The fact that the kernel is just containing 0. We proved most of this today. Well, we proved even more of this today. So we've proved the equivalence of that essentially in chapter 5. The same proof works here. But here's the new one. If S is a subset of V, it implies that L of S is a linearly independent subset of V. But not just for one subset. If you have that for all subsets, if you have the image of all linearly independent subsets are once more linearly independent images, that is another condition that serves to capture injectivity of L. So it's a little bit subtle, but the proof is there. Now, this isn't really much different than what we did back in chapter 5. The sum, difference, and scalar multiple of linear transformations from vector space V to vector space W is yet again a linear transformation from vector space V to vector space W. And proof is just basically the same as it was in pre-calculus. You know, why is f plus g a function if f and g are functions? Because if f of x is single valued and g of x is single valued, then f of x plus g of x is still a single value. And also it filters through the linearity condition. So the sum, difference, and scalar multiples of linear transformations from V to W are once more linear transformations from V to W. Hey, that means that the set of linear transformations from V to W is itself a vector space, right? Because it's closed under addition and scalar multiplication. So it's actually a subspace of the set of all functions from the set V to the set W. It's kind of a new example of a vector space. We can live it out there, but there it is. Here it is stated as a proposition. Basically, this again is my notation for the set of all linear transformations from V to W. That is a particular subspace of all functions from V to W. Functions from V to W can contain all kinds of weird stuff, like nonlinear functions. You know, you can take sine, like the SINE of like the, I don't know, you can do all kinds of crazy stuff. All right. Composition still makes sense. And if you had a linear transformation from V to U and another one from U to W, you can talk about the composition of S and P itself being a linear transformation from V to W. And you can still prove that the composition of linear transformations is much more a linear transformation. The proof I gave you in Rn still works here. Okay? And so what that means then is if you look at the set of linear transformations from, by the way, from the vector space to itself, you can add those, you can subtract them, you can scalar multiply them. You can compose, if you have a linear transformation from a vector space to itself, right, you could compose that with another such thing and get another such thing, right? So if you take the composite of something that goes from V to V, something else that goes from V to V, you'll get yet another thing that goes from V to V. So that gives you a way of, let's say, multiplying transformations. So if you have a vector space together with an addition, well, I mean, it's vector space, together with a multiplication. Multiplication is like some way of putting together two things in the vector to get another vector, right? Not addition, but some new operation. In this case, function composition. Then you get what's called an algebra. So you guys have seen two examples of algebras in here so far. The one is just matrix. Square matrices. Multiply square matrices, get another square matrix, right? But you can also, they also has a vector space structure, you can add them. So n by n matrices forms an algebra. But also you can look at just linear transformations from a vector space to itself. That's also an algebra where the multiplication is given by, what's the word? Composition. We'll come back to that from time to time in here. But yes, sir.
So with an algebra, like anything like that kind of defines how you can add or subtract or like different operations in a certain subspace or something.
In a formal sense, an algebra is simply a vector space paired with a multiplication that respects the vector space structure in a certain technical sense. But okay. Oh. Yeah.
But that multiplication must be like not scalar multiplication, but like times itself.
Right. Some. I mean. Yeah.
So it's closed under multiplication?
The algebra?
Yeah.
Yeah. The multiplication has to be back into the vector space again.
Okay.
Yep. Okay. So put this away. I didn't want to write that stuff out because it's pretty much, we've actually written those things out. They flow over in the context of column vectors. The thing about this state for you is so important. I mean, these are useful, of course. And by the way, this gives you yet another tool to show something's a subspace, right? If you can write down a function, which is clearly a linear transformation, right? And if that linear transformation takes the thing you're looking at as its kernel, or the thing you're looking at as its range, then by this corollary right here, that proves it's a subspace. You're like, well, there's a lot involved to prove something is a linear transformation. There's a lot involved to prove, that the thing you're looking at is the kernel or the range. Well, that's true. If I actually made you work out all those details, that would be still kind of onerous. But I'd have to really, really be a jerk to not give you a lot of credit for showing me that the given space you're looking at is the kernel of something or the range of something. Like, that would just be a jerk move on my part. Because to show me that something is the kernel or the range of a mapping shows to me that you have a deep understanding of linear algebra. Far deeper than, say, just the rote application of a subspace. My brother worries about this. He says that he's afraid if students learn this too early, then all problems become too easy for them. So.
Why is that something to worry about? I don't understand.
Well, it's like you try to ask a question on a test which has some kind of difficulty, right? But if the student really understands the comment I just made, they can just write down a formula and be done. It's kind of dangerous though, right? You have to really understand what you're doing.
Sometimes.
Sometimes the word you like, yes. So here's the proposition theorem. If you have beta, a basis, You're like, ah, basis, finally back to that again, yes. If beta is a basis for a vector space V, then if L is a mapping from beta to W, so a function, right? Right? Then there exists a unique, let me call this L tilde, okay? Then there exists a unique L from V to W such that L restricted to beta is equal to L tilde. Yeah.
Is the exclamation point relevant?
Unique. There exists a unique. All right. I have now undone the usefulness of the shorthand.
Sometimes shorthand is like more trouble than shorthand.
That's up to you, but yes. That was actually not an insult.
I mean, it wasn't meant to be, but it still hurt.
This is why we can't have these things.
I feel like notation is like one of the biggest struggles I have in this course, which is silly.
Oh no, it's not silly. Actually, a major part of this course is learning the notation. It is one of the quintessential struggles of the linear algebra student, is to internalize the notation and understand it. Yeah.
Speaking of internalizing the notation, what's the bar with the little p at the end?
This is the restriction of L to beta.
Oh, that's beta. Okay.
Right.
That's
L.
beta.
What's that? Oh, I'm sorry?
Your beta was so far.
Oh.
Yeah.
Oh, okay. I will accept this criticism. All right, let's go on here. So let L tilde from beta to W be defined by L of VI equal to CI for all I equals to 1 to n, all right? And this CI is just, these are just the numbers. You see, beta is a finite set, right? It's a basis. So there's as many things in beta as there are dimension of n. I mean, this could be clear of finite, okay? I mean, we haven't talked really about infinite basis, so whatever. Every dragon's there. Let's see where we are. So I equals 1 to n. These are constants. They define L tilde like that. Okay? Now, I claim that there exists a unique function on all of these. So one way to show something exists uniquely is simply to write a formula for it. Here's my formula. L of V equals to L of what? The sum of VI, oh, stink. The basis, I'm using V for the basis. I was letting beta equal to V1 through Vn if you hadn't noticed. So let's say L of X, V is a bad letter. L of X, X of I, V spy, right? You agree? If V is beta is a basis, you can expand X in the basis, right? So this is going to be defined to simply be the sum I equals 1 to n of xi L of vi. Of course, to be more explicit, this was what? Ci, right? Yeah.
Did you mean to write V sub I, C sub I there? With your definition of L tilde?
Well, I'm defining L right now. So this is actually the definition right here. Yeah, right, it's not right there. That serves as a definition because any x can be written in terms of its coordinates with respect to the basis. So I'm just saying you pick off the components for the coordinates and you just multiply by the No, it's the CI. What is it? It's L tilde of VI, right?
Okay.
So in particular, if you look at
Okay.
if you look at L of just VI, then what are the coordinates of VI? It's everything is 0 except for the ith one, right? So this just becomes 1 times CI, which is what? L tilde of VI, which goes to show you that L and L tilde agree on the basis since I was arbitrary. So, remark, we refer to this proposition often later. This is known as linearly extending L from its values on the basis. You've already seen examples of this in action, right? Where did you see this before? How do you define a linear transformation? You can define a linear transformation is uniquely defined by its standard matrix, right? How do you find the standard matrix? All you need is the values of t on E1 through En. I'm just saying that that also is true in general, even though there's no matrix here. Not yet, anyway. There was supposed to be a matrix here. Well, if I find time today, I'm going to tape another bit for you to watch so you can do the homework, which has been extended to Friday, right? But I have a lot of questions about coordinates and finding the matrix of linear transformation, right? So I'm going to try to take about an hour today, which is very calculational. It will help you do the homework, okay? Who knows, I might even solve a homework problem in this thing I'm taking.
Is there like, I'm
We
really
gotta start
disappointed
it.
that there was, well, I was disappointed that there was like no examples today, like, and it's just,
That's what he's saying. He's saying trying to put examples on the video.
alright. Looking forward to it.
All right, at some point in linear algebra, we have to do linear algebra. This is linear algebra. Linear algebra is the study of linear transformations on vector spaces. So this is actually linear algebra.
They're a closed under multiplication. It's just their algebra.
Well, that's the.
I'm still trying to wrap my hand around that, like, maybe I'm behind everyone else, but like, what do you mean by that?
So this thing. You guys can go. I'm just talking about.
You're not really talking about.
You know,